Good morning, class. We are looking at exam 2 review covering chapter 3, differentiation rules, section 3.1 to 3.8. Here's part 1 covering from section 3.1 to 3.3, section 3.1, derivatives of polynomials and exponential functions, 3.2, the product and quotient rules, 3.3, derivatives of trigonometric functions. So we will cover chapter 3 differentiation rules, and for this exam from 3.1 to 3.8. The rest of them will be covered in the next exam. So what have we learned? As far as differentiation formulas are concerned and the definition, dy dx, or the limit of delta y over delta x as delta x approaches 0, or f prime of x equals limit of f of x plus h minus f of x over h as h approaches 0. This is the definition, everybody. Now, we are going to go with differentiation formulas. No need to use the differentiation definition, which is going to make it much easier. The derivative of x is 1. The derivative of c times f of x, you can take the c out. d dx of f of x plus minus g of x is d dx of f of x plus minus d dx of g of x, which means the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. We need these formulas. You can see the proof for those in your lectures. The limit of sine theta over theta as theta approaches 0 is 1. The limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. E, as you know, is just like pi, and it's an irrational number. It has a specific definition. E equals the limit of 1 plus 1 over m to the power of n as n approaches infinity. Or E is a number such that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. Now here's some of the differentiation formulas we'll be using. The derivative of a constant is 0. The derivative of x to the power of n is n x to the power of n minus 1, known as the power rule. The derivative of k times x is k, where k is a constant. The derivative of sine is cosine. Cosine is negative sine. Tangent is secant squared. Cotangent is minus cosecant squared. Secant x is secant x tan x. Cosecant x is minus cosecant x. Cotangent x. Now, we are looking at the product and quotient rule. In this case, f g prime is f prime g plus g prime f. F over g prime is f prime g minus g prime f over g squared. This is a shorthand notation. And if you have memorized it in a different order, that's fine. This one is the same thing that was mentioned here. The c comes out, and these two refer to this formula. The derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. So this have been discussed, and we have more formulas, and we're going to discuss them later on, but this one is the extended power rule, also known as the chain rule. So the derivative of g to the power of x, g of x to the power of n is n, g of x to the power of n minus 1 g prime. The derivative of e to the power of x is itself. The derivative of e to the power of kx is k times e to the power of kx, if it's e to the power of jx, by g of x, e to the power of g of x. The derivative is g prime of x times e to the power of g of x. And they're all by the chain rule. And I will go over the last two later on when we look at those. And in fact, I want to quickly look at the proof. And these are composite functions and the chain rule. As you recall, y equals f of g. That means f of g of x. So if you want to differentiate that, becomes f prime of g of x times g prime of x. In a Leibniz's notation, dy dx is dy du dx. If you're dealing with a natural log, the derivative, you just flip it over, 1 over x. If it's natural log of a function of x, such as u or g of x, you flip it over and times g prime of x or the u dx by the chain rule. There are more that I will discuss later on. And these are the inverse trigonometric functions. The derivative of sine inverse is 1 over square root of 1 minus x squared. For cosine inverse is the same thing with the negative. Tan inverse is 1 over 1 plus x squared. For cotangent inverse is the same thing with negative. Secant inverse, the derivative is 1 over x squared of x squared minus 1. And for cosecant inverse, the same thing with the negative. I will discuss this further as we go through them, but I just wanted to give you the synopsis of what's going on. The idea is, now that we use the differentiation formulas instead of the definition, it's going to make life easier. As an example, on this page, if I want to differentiate y equals x to the power of 1000, this is the first example, I'm going to use the power rule. So 1000 sits in front and becomes the coefficient. And then we subtract 1 from that, becomes 999. And you're done. It's that simple. Instead of using the definition. If I want to differentiate y equals 3r squared, the 3 remains. So I'm going to write y prime is 3 times, now r squared is 2 times r to the power of 2 minus 1, or simply 6r. Now, what I want to mention is the notation dy dr and ddr of 3r squared, because we have different notations for differentiation, y prime, f prime, ddx, which makes it the Leibniz's notation. Normally, we are under the assumption that we use x as the independent variable, and we do most of the time. But there may be others, such as t or theta, or in this case, r. So when we write y prime, it's fine. But dy dr is telling us precisely what is the independent variable. So it's a different notation when it comes to the differentiation. Now, let's do this one by one. This is 8x to the power of 7, because basically what happens is 8 sits in front. 12 times 5, because 5 gets multiplied by 12. 60x to the power of 4, minus 4 times 4, minus 16x cubed, plus 10 times 3, 30x squared. Minus 6x results in minus 6. Okay, we are looking at this one. This, kx, the answer is k. And 5, a constant, any number, the derivative is 0. So this is the final answer, everybody. Now, in this page, we are going to use the power rule again. However, just the way it is, square root of x has to be changed to x to the power of 1/2, so we can use the power rule. Now, when we distribute, this is x to the power of 1, and these two, a to the power of m times a to the power of n is a to the power of m plus n. They become x to the power of 1 plus 1/2, or 3/2. The rest is very straightforward. We have sits in front, x to the power of subtract 1, 1/2, plus 5 minus 2 results in 0. We don't write it. And x to the power of 1/2, we can take it back to the square root. Again, just the way it is. I cannot use the power rule. So what do I do? I'm going to write 2 over 9 x to the power of 5 minus 9 or to the power of negative 4. So I bring it up so I can use the power rule. Again, reminding you of a to the power of m over a to the power of n is a to the power of m minus n. And now 2 over 9 times negative 4. So let me show you how it's going to work. F prime is 2 over 9 times negative 4 x to the power of minus 4 minus 1, which is negative 8 over 9 x to the power minus 5, and it becomes minus 8 over 9 x to the power of 5. And the last question, please recognize pi squared is a number, and therefore the answer is 0. Meaning, if I want to take the derivative of any number, pi squared, e, 2, 5, 1.1, 2/3, makes no difference. The derivative is 0 because you're dealing with a constant. And that's the key, everybody. You're dealing with a constant. So that's taking care of some basic differentiation rules. The derivative of a constant is 0. The derivative of k times x is k. The derivative of x to the power of n is n x to the power of n minus 1, known as the power rule. Now we want to go with the product rule. Now, product rule, here's the shorthand notation. F g prime is f prime g plus g prime f. The reason I use that, because for the quotient rule, I use the same thing and I change the sign to negative and I put the g squared at the bottom. So if I want to differentiate this, I'm going to write this formula from the memory, because you got to memorize the formulas, okay? There's no such thing as formula sheet, okay? So you memorize this. So I would write the formula next to me and I would follow that. So I'm going to give it a name. The first one, the first function, I'm going to call it f. The second one, I'm going to call it g. So I need f prime, which is going to use the power rule per term. 4x cubed minus 6x squared. This goes to 0 times g, just put the second parentheses, plus g prime 6x minus 5, that's the g prime, times f, just write the first parentheses. And believe it or not, you are done with calculus. Of course, this is a warm-up example, which means you're going to finish it on your own. We are completely done with calculus. You take a few algebraic steps to finish the job. A few algebraic steps. Differentiate y equals x squared sine x. Notice I put a raised dot in between and make sure everybody realizes this is using the product rule, and I'm going to call this f times g function. So according to this formula, I need f prime, which is 2x times g, which is sine x, plus g prime, the derivative of sine x is cosine x, the derivative of sine is cosine, and then times f, which is x squared. Now, you have to bring the x squared in front, otherwise it's awkward. One may be under the assumption that it's cosine of x cubed. Definitely bring the x squared in front. That is extremely important. Here's a warm-up example for the quotient rule. And I'm going to call the top function the f function, the bottom one is the g function. And this is the formula. I'm going to write the formula because sometimes I've seen students using d dx of this times d dx of that, and that's fine, but it takes a long time and sometimes it's hard to follow. Write this formula, which is a shorthand notation. We need f prime. So we need 4x cubed minus 6x squared times g, just write the denominator, minus g prime, we need the derivative of the denominator, which is 6x minus 5, times f, the top function, the numerator next to it. And in the denominator, you put the same denominator and square it. So you put it in a parentheses, squared. It's that simple. And of course, we're done with calculus. Now you use your algebraic techniques to finish the job. F of x is example 4. F of x equals 10x squared minus 7x cubed over x squared. Differentiate. Do we need to use the differentiation rule? And that's important to understand. If you need to use a different quotient rule like this one, and you try to avoid it, most likely you make it more difficult. If you don't need to use the differentiation rule, the quotient rule, and you use that, the same thing, and in many cases you don't end up with the correct answer. So you make up two fractions. Here's one, 10x squared over x squared, which gives you 10. Here's another one, minus 7x cubed over x squared, which gives you minus 7x. And clearly you see that f prime of x is just minus 7. So you're done in one shot. Extremely important to pay attention to this rule. Whenever you need a quotient rule, please use that. And if you don't need it, understand your algebraic technique will help you get to the answer much faster. All right, we want to find the limit of sine 3x times sine 5x over x squared as x approaches 0. It's important to know that we have to follow what we have learned. For example, we used differentiation definition. We couldn't use the differentiation formulas that we are learning in the previous exam. Same thing here. For example, L'Hopital's rule is coming up and we can't use it yet. So instead, I'm going to remind you of what we have learned. The limit of sine theta over theta equals 1 if theta is approaching 0. And the limit of cosine theta minus 1 over theta is 0 if theta is approaching 0. So we use these two to see what we can do with this one. We notice that, by the way, it's important to understand the meaning of this. This one, and this one must be the same. That means the argument of sine, whatever it is, must be the same as the denominator, the same as this piece that is approaching 0. So for example, if it's x, this is x, x, x. If it's 5x, 5x, 5x. So let's see what's going on. If we throw in number 3 here and number 3 here, because we need a 3x, and then 5 up here and 5 down here. Let's see what happens. We are separating these two into two fractions, where one of them is sine 3x over x, one of them is sine 5x over x. And when you compare, you notice if this is 3x, we are hoping to have a 3x here. Okay, I can put the 3 down here and up here. Over here, the argument is 5. We hope we have a 5 here. So plug in 5 and plug in 5 up here. It's important to know this is 1, this is 1. Now, we are going to separate these two. As we separate this one, we can take the 3 out. And we separate this one, we can take this 5 out. So it looks like that. Now, it is important to know when x goes to 0, so does 3x, so does 5x. And this and this and this must be identical for this expression to become 1. Same thing here. The argument of sine, the denominator, and this one must be the same for this expression to go to 1. So we have 3 times 1 times 5 times 1, which makes it 50. So this is the justification, and this is the proof. The limit of cosine theta minus 1 over sine theta as theta approaches 0. Since we have this one, and this doesn't look like that, the technique is to recognize if I divide this one by theta, it looks like this, so I'm going to divide the top and the bottom by theta. Because I'm doing it to both the numerator and denominator, I'm not changing the essence of the fraction. Therefore, I'm going to take the limit of the top as theta approaches 0 and the limit of the bottom as theta approaches 0. This will be replaced with 0. This will be replaced with 1, and 0 over 1 is 0. So we proved the answer is 0. Example 6, find the limit of cosecant x, sine of sine x as x approaches 0, we want to find. And so we know that cosecant x can be replaced with 1 over sine x. So this becomes the denominator of this as sine x. Notice, x is approaching 0. Since x approaches 0, so does sine x. Okay. And what you can do, you can change this one now to sine x and see the result. Or you can say, okay, let sine x be replaced with theta. So let sine x be replaced with theta. So sine of theta over theta, and we said x approaches 0, that means sine x approaches 0. So this one we change it to sine x and therefore theta. And according to this, the answer is 1. The limit of sine x squared over x as x approaches 0. This seems something similar to that. So here's the manipulation we are going to do. You cannot change the argument of trigonometric functions. So it's sine of x squared. We want to make sure everything else looks like that. So how can I change this to x squared? Well, I can multiply the top and the bottom by x. So This is one piece, and this is another one. So the limit of x as x approaches 0, and the limit of sine x squared over x squared as x approaches 0. But remember, when x approaches 0, so does x squared. That's why this one we keep it as x, and this one we change it to x squared because we want these three to be identical. Now, you don't even have to change it to theta, but please understand the meaning of this is that the argument of sine, the denominator, and this that goes to 0 must be identical, and they are. So this goes to 0, this goes to 1. The product of 0 and 1 is 0. Derivative of trigonometric functions prove that the derivative of tan x ddx of tan x is secant squared, so your function y or f of x is tan x. Now, as the derivative of sine x equals cosine x, you can find it in the lecture notes. We use geometry, trigonometry, algebra to prove that, and the limits that we had in the previous pages, the limit of sine theta over theta as theta approaches 0 equals 1, the limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. We use those, and we get to the fact that the derivative of sine is cosine, the derivative of cosine is minus sine, and of course, as I said, trigonometry is involved. After those two, the rest become very easy. So how do we go by proving that? We are going to use the trigonometric identity tan x is sine x over cosine x. So I'm going to remind you that tan x is sine x over cosine x over 1 over cotangent x. Cotangent x is cosine x over sine x over, or 1 over tan x. Secant x is 1 over cosine x, and cosecant x is 1 over sine x. So why am I using that? Now I can use the quotient rule. F over g prime is f prime g minus g prime f over g squared. So the top is f. I need f prime. The derivative of sine is cosine x times g, just the denominator, which is cosine x, minus g prime minus the derivative of cosine is negative sine. So minus negative sine x times f times the top, which is simply sine, and then put the bottom g, which is cosine x, and square it. And this is the only calculus step. As you can see, this is cosine squared plus sine squared. Cosine squared and sine squared, they add up to 1. So we get 1 over cosine squared, and because secant is 1 over cosine, then 1 over cosine squared must be secant squared. So what did we use here? One of the Pythagorean identities, which says, let me use a different color that makes it easier to read. Sine squared plus cosine squared equals 1. Y equals secant x. The derivative of secant x is secant tan x, and we're going to prove that. And to do so, we are going to use the fact that secant x is 1 over cosine x. And we're going to call this f over g and use the quotient rule again. To do so, we need f prime, the derivative of the top obviously is 0 because you're dealing with a constant and you multiply it by the bottom, which is cosine x, f prime g, minus g prime minus the derivative of cosine is negative sine f times 1. And the bottom, just write it squared, cosine squared. Of course, this is 0, this is a positive, so we get sine x over cosine squared x. As you recall, we've done these tricks in trigonometry. We're going to write this as 1 over cosine and then sine over cosine. 1 over cosine is secant x. Sine over cosine is tan x. So secant x tan x, which proves the derivative of secant x is secant x tan x. Differentiate y equals 1 plus sine x over x plus cosine x. We are going to use the quotient rule. F prime g minus g prime f over g squared. Again, if I'm differentiating this, first I'm going to write the formula next to me and follow that. And so we have what? The top gives me cosine x. When I differentiate, this is 0, this is cosine x. Times the bottom, I just put the bottom here, g, x plus cosine x, minus g prime, this is 1, plus cosine gives me negative sine, so 1 minus sine x, that's g prime times f, which is 1 plus sine x. And I just write the bottom g in a parentheses and square it because I need g squared. And again, I'm done with calculus. We are going to continue with our algebraic steps and trigonometric steps. So what we are going to do, we are going to distribute this. We get x cosine x, and this one gives us cosine squared. What happens here? You have a minus b times a plus b, which is a squared minus b squared, or 1 minus sine squared. As I mentioned, the Pythagorean identities, sine squared and cosine squared is 1. That means 1 minus sine squared is cosine squared, 1 minus cosine squared is sine squared. And you can replace this with cosine squared. What I want to mention here, that if you divide this one, both sides, by cosine squared, you get this one, tan squared plus 1 is secant squared. If you divide both sides by sine squared, you get 1 plus cotangent squared is cosecant squared. Those are known as Pythagorean identities in trigonometry. These two cancel each other. And the numerator is left with x cosine x only. The denominator doesn't change. You don't have to raise it to the power of 2. And you're done. Differentiate y equals 1 minus secant x over tan x. I'm going to call it f over g. I'm going to write the quotient rule for differentiation, and I'm going to follow that. So I need f prime at top. 1, of course, is a constant and gives me 0. Secant x gives me secant x tan x. We keep the negative sign, so minus secant x tan x. Okay, minus secant x tan x. We're going to multiply it by g, just by tan x. And then minus g prime, the derivative of tan is secant squared. So minus secant squared minus secant squared times f, just in a parentheses next to this, put the numerator, which is 1 minus secant x. Then tan x at the bottom, square it, make it tan squared x. And again, done with calculus. So we have negative secant x tan squared minus secant squared x plus secant cubed x. The denominator doesn't change. Everything in the numerator has a factor of secant x, so we take it out. Gives us negative tan squared minus secant x plus secant squared x. Everything else remain unchanged. One of Pythagorean identities in the previous page gave us 1 plus tan squared equals secant squared, or tan squared plus 1 is secant squared. Makes no difference. If I move tan squared to the right, I get secant squared minus tan squared. Secant squared minus tan squared equals 1. So this one and this one combine into 1. They will be replaced by 1. We get secant x times 1 minus secant x over tan squared x, and we are done. Sometimes in some cases, especially when we were dealing with trigonometric identities, all of this could be changed to sine and cosine. You don't need to do that here. We want to differentiate cosine x over 1 minus sine x. And again, we are going to rewrite this as f over g in this format, meaning quotient rule is going to be used. So we need f prime g. So we need the derivative of cosine, you know, it's negative sine, times g, that means just write the denominator next to it, times 1 minus sine x, minus g prime minus, this is a constant and 0, minus sine x, the derivative is minus cosine x. So minus is this sine, and then this gives you minus cosine x, and then now the top sits next to it, means times cosine x, and you just write the bottom squared. You don't have to square it, just write it in a parentheses and square. Now we are going to distribute, and we get minus sine x plus sine squared, minus and minus, plus cosine squared. So we get minus sine x plus sine squared plus cosine squared over the denominator, 1 minus sine x squared. And notice these two, sine squared and cosine squared, they add up to 1. So let's replace it. And let me rewrite this so it becomes clear as to how I did that. So this is 1. I'm going to put the 1 first. 1 minus sine x. And this is 1 minus sine x. Quantity squared. This, you can drop one of those factors of 1 minus sine x. The numerator changes to 1, and the denominator is 1 minus sine x. And I hope you see again, we have a bunch of algebraic steps as well as trigonometric steps. Find an example number 2. Find an equation of a tangent line to the graph of the function y equals e to the power of x cosine x at 0, 1. In order to find an equation of any line, we need two things. We need a pair x comma y is given. We also need the slope, which is not given. So the methodology is to first and foremost differentiate, then plug in 0 to find the slope. To do so, I'm going to put a raised dot in between and call this f times g, and I'm going to use the product rule. So immediately, I'm going to write the shorthand notation of the product rule. Fg prime is f prime g plus g prime f, and I'm going to use it. If you get to the habit of doing that, not only you memorize the formulas faster, differentiation becomes a lot faster than writing ddx of this and ddx of that. So I need f prime, which is e to the power of x itself times g cosine x minus, my apologies, plus g prime, the derivative of cosine, so plus negative sine x times f times e to the power of x. So we get e to the power of x times cosine x minus sine x times e to the power of x. So this would be f prime g plus g prime f. Bear in mind that the derivative of cosine is minus sine. So this is a plus. We're going to factor the e to the power of x out. And in order to find the slope, we are going to plug in the x coordinate, which is 0. And that means we get e to the power of 0 cosine of 0 minus sine of 0. So e to the power of 0 is 1, cosine of 0 is 1, sine of 0 is 0, the answer is 1, and so m equals 1. And because this is the y-intercept, therefore this is b, we are going to use the easy way out. Y equals mx plus b. It so happened m as well as b are both 1. Again, m is 1, we just found it. B is given as 1. Why is this b? Because this is the y-intercept, everybody. So you don't have to use y minus y1 equals m times x minus x sub 1. Find the points for which the tangent lines are horizontal. Speaking of the tangent line, in order to find the slope of a tangent line, first you have to differentiate. So speaking of the tangent lines, because of this, we are going to find f prime of x, which is 3x squared minus 6x. Because these lines are horizontal, their slope must be 0. We set this equal to 0. So again, we want to find points for which the tangent lines are horizontal. Tangent lines, we don't have any information. We differentiate f of x. F prime of x is 3x squared minus 6x. Because they are horizontal, and we know the slope of any horizontal line is 0. Horizontal lines, the slope is 0. So set this equal to 0. That means you factor the 3x out. So 3x times x minus 2 is 0. Therefore, either x is 0 or x is 2. It's important that we are looking for pairs. we should know we are looking for pairs. So if you put the 0 into the original function, gives you the pair 0, comma 5. If you plug in 2, 2 cubed 8 minus 3 times 2 squared, 12, 8 minus 12 minus 4 plus 5 is 1. So plug in 2, it gives you 1. These are the pairs, and you have to write them in pairs.